So in the last video, we saw circuits, or circuit diagrams to do addition of at least 1 bit. In here, what I want to do is I want to talk to you about writing those circuits in a different notation. In fact, I want to write those circuits as functions, and really they are functions, right? I mean, the gates are simply like logical connectives, ands, ors, nots, and XORs, and so on. And the wires carry either 0 or 1, right? They're like variables that have either 0 or 1. And the output is another wire, which is just another variable. So those circuit notations, as long as they don't have feedback loops, okay? If they're just simply inputs, bunch of gates, outputs, they really are just logical functions. And we can write those in any notation for functions. Like, for example, I could put tables that say what the inputs are and what the output should be. I can also just write them as mathematical functions, which is what we're going to do here. So these are our gates, okay? So what we have here is XOR, and remember XOR looks kind of like this. That's probably the world's ugliest XOR, but we have an XOR gate for A, B, and then A XOR B, okay? And I can actually just write that as a list function. So if B1 is equal to 0, then it's just the value of B2, right? Because 0 and 0 XOR 0 is 0, 0 XOR 1 is 1. So it's just whatever B2 is. On the other hand, if B1 is not 0, so it's equal to 1, then if B2 is 0, we want to return 1, otherwise we want to return 0. So that's our expression, mathematical expression of XOR, okay? Likewise, we can do AND. If B1 is equal to 0, then the result is 0, because, false on anything is false. Otherwise, if B2 is equal to 0, then it's still 0, because it's false. And the only possibility left is 2 1s. So this definitely captures AND, okay? And then we have OR. And in the case of OR, if B1 is equal to 0, well, if B1 is equal to 0, then it's just whatever B2 is, right? So if B2 is 0, we return 0, otherwise we return 1. And if B1 is not equal to 0, so that B1 is actually equal to 1, then absolutely what we're going to do is just return 1, okay? So here we have A or B, we have A, B, right? So these gates can actually just correspond to code, okay? Let's take a look at a more complicated kind of expression. We have here the half adder, okay? And if you remember the half adder, we had B1 coming in, okay? And B2 coming in. And then we're just going to connect those. And we're going to connect those into an XOR, right? And that's going to give us the sum, okay? And then we took B1 and B2 and we also connected them with an AND, and that gave us the carry, okay? So that's what we're doing here. We're actually using those previous functions that implemented gates and saying, oh, take B1 and B2, take the AND to get the carry, the XOR to get the sum, and then we'll return that in a list, right? Because we actually have 2 outputs, okay? This one's the more complicated circuit, is the full adder. And I'm introducing a new kind of notation, which is let star, okay? And let me quickly tell you what that is. I mean, this is basically a bunch of assignment statements. So what this says is that H1 is equal to half adder of B1 and B2, okay? So you might write this in a different language, like Java, for example, okay? And then you would say that C1 is equal to the first of H1, and you would say that S1 is equal to the second of H1, and so on, right? That's what this notation means, okay? There's only one restriction, and that is that this was known as a single assignment. You can only assign to the variable once. So if I were doing this in Java, I may have to say something like final, some kind of type here, let's say adder result, right? H1, and then final bit C1, final bit S1, and so on. And the final keyword tells me I can't assign to it anymore, okay? In C++, you would use const, okay, to do that. So that's what these assignments are. Basically, just call the half adder on those incoming bits B1 and B2, right? And then we'll do the second half adder. And notice that we're doing S1, which we actually got from the first half adder. So that's how we connect those two, right? Using the same variable. In the circuit, we just drew a line between them because it was the same wire. And then the output is just this. The sum is whatever the sum of the second half adder is, and then the carry is the OR of the two carries, right? Just like in the original full adder circuit. So what we've achieved is this. We wrote down circuits for adders, and now we've written down functions that mimic those circuits. Now, why would we want to do this? Because we're going to be able to prove properties about these functions. And those properties then should also be true about the circuits.